I'm going to do the first half of this AIME. You can find links to all the problems in the video description. Let's let n be between two numbers, a and b. Here we have n is 22% less than b. This simplifies to 39 over 50 times b. Multiplying by the denominator, we have that b is a multiple of 50 because 39 does not contain any of the same primes as 50. For the same reason, n is going to be a multiple of 39. N is also 16% greater than this other number a. This simplifies to 29 over 25 times a. Multiply by the denominator. Again, 25 and 29 do not share any primes in common. So a is a multiple of 25 and n is a multiple of 29. We can set these two equal to each other. 39x equals 29y. These are all integers and there are no primes in common between 39 and 29. So our solution is x is 29 and y is 39. N is the product of these two numbers, which is 1131. In mod 1000, that's 131. Let's go to problem 2. I find it easiest to just make a table. We have students who are taking Latin and students who aren't taking Latin, and we're dividing them up by year: freshman, sophomore, junior, and senior. Since we only care about percentages and fractions, let's just pick an arbitrary size for our school. We'll say there are 100 students to make it easy. 40% of them are freshmen, 30% are sophomores, 20 and 10 for juniors and seniors. All the freshmen have to take Latin, so we put 40 here and 0 here. 80% of our sophomores are still taking Latin. That's 24, leaving 6 who aren't. Half of our juniors are taking Latin, and 20% or 2 of our seniors. Adding this first column, we have 76 students total who are taking Latin. 24 of them are sophomores. So our probability is 24 over 76. This simplifies to 6 over 19. The problem wants m plus n, and our answer is 25. Let's go to number 3. First, let's check the 2-digit multiples of 17. And none of these satisfy the requirements. So let's look at 3-digit numbers with a in the hundreds digit, b in the tens digit, and c in the units digit. And we'll call this m. We want m to be a multiple of 17. This puts a in our hundreds digit, 10 times b is in our tens digit, and c by itself. And then we also have the digit sum, a plus b plus c, is also equal to 17. We'll subtract these two equations and factor out the 17 on the left-hand side. We have 99a and 9b on the right, and we can factor out 9. All of these variables, a, b, and x, are integers. Since 17 and 9 don't have any primes in common, then we have x minus 1 is a multiple of 9. So let's try various multiples of 9 and see what works. If x minus 1 is equal to 9, then m is equal to 17 times 10, or 170. This digit sum is 8, and we need 17. Let's try x minus 1 is equal to 18. Then m is 7 times 19. This is 323, and our digit sum is 8 again. We'll try x minus 1 is 27. M is 17 times 28. This product is 476, and our digit sum is 17. So our answer is 476. Now we'll do number 4. Let's draw our isosceles trapezoid and draw an altitude. The prime factorization of 192 is 2 to the 6th power times 3. So the log of 192 is 6 log 2 plus log 3. Similarly, log 16 is 4 log 2. Let's label this right triangle over here ABC. One of our bases has length log 3. This base is 6 log 2 plus log 3. With the symmetry of this trapezoid, we can find the length from B to C by taking the length from B to D, subtracting log 3, and then multiplying by a half. That means BC has length 3 log 2. This altitude AC has length 4 log 2. So triangle ABC is a 3, 4, 5 triangle. So the distance from A to B is 5 log 2. Now we can find the perimeter of our trapezoid. And we'll substitute and then use our rule for logarithms to turn these sums into the log of a product. We have log of 3 squared and log of 2 to the power of 16. This gives us P is equal to 16 and Q is equal to 2. The problem asks for P plus 2 and our answer is 18. Let's go on to number 5. This will be easier to solve if we consider smaller cases. Let's see what happens when n is equal to 3 and see if we can generalize from that. This is a 3 by 3 grid of unit squares, and let's look for squares that are adjacent. So these two are adjacent and these two are adjacent. Each row has 2 pairs of adjacent squares. We get that from n. That's 3 minus 1. That's per row, and we have 3 rows. The same quantity is true for our adjacent squares oriented vertically, so we'll multiply that by 2. That's the numerator of our probability. The denominator is just 9 choose 2, the number of ways of choosing 2 squares out of 9. If we generalize this for any value of n, we can see that each row is going to have n minus 1 horizontally oriented adjacent squares. There are n rows, and it's the same count for vertically adjacent unit squares, so we multiply this by 2. The denominator is the number of squares, which is n squared, choose 2. We need this probability to be less than 1 over 2015. And from here, we can find our bound for n. Our denominator becomes n squared times 1 less than n squared all over 2. Let's simplify this fraction. And we note this difference of squares factorization in the denominator allows us to cancel this factor. We can also cancel one of the n's. And we're left with 4 over n times n plus 1. And we want this to be less than 1 over 2015. Multiplying by the denominators, we have this product is greater than 8,060. We can ballpark this by noting that 90 squared is 8,100. So let's try n equals 89. Then n times n plus 1 is 89 times 90. That's 8,010, which is too small. So let's try n equals 90. That's 90 times 91, or 8190, which is valid. So our least value of n is 90. Let's go on to number 6. Let's factor 2 from our polynomial, and we'll apply Vieta's formulas in terms of the roots r, s, and t. We'll set the corresponding coefficients equal to each other. R plus s plus t is equal to a, and 2 times this sum is equal to a squared minus 81. And then 2 times this product is equal to c. We have an a squared over here, so let's square this equation. And we can make this substitution. And since this was equal to a squared, we have that the square of these terms is equal to 81. In the problem statement, we're given that these 3 roots are all positive integers, and that a and c are also positive integers. So let's see what values of r, s, and t satisfy this equation. We'll make it a little bit easier by listing out the perfect squares. Let's start with 81 and subtract some smaller perfect squares, like 64. This leaves 17, which is the sum of 2 other perfect squares, 16 and 1. Again, a is the sum of these roots. So a is 8 plus 4 plus 1 is 13. Let's take our sum 81 and subtract 49. This is 32, which can be written as the sum of 4 squared and 4 squared. So our roots are 7, 4, and 4. Our value of a is 15. If we take 81 and subtract 36, we get 45, which is also the sum of 2 perfect squares, 36 and 9. So these roots are 6, 6, and 3. So when Steve says, here's the value of a, and John says there are 2 possible values of c, we're looking at a equals 15. Let's calculate our 2 possible values of c. C is the product of our roots times 2. For our first set of roots, c is equal to 224. For our second set, c is 2 times 6 times 6 times 3. That's 216. The problem asks for the sum of these 2 values. This gives us our answer, 440. Let's go to problem 7. Here's our rectangle, PQRS, inscribed in our triangle with side lengths 12, 17, and 25. Since we know our side lengths, let's use Heron's formula to calculate the area of triangle ABC. We'll start by finding the semi-perimeter, which is 27, and then plug it into the formula, subtracting the 3 side lengths. Taking the square root, we have that the area is 90. PQ has length W. We can use this area to find the length of this altitude from vertex A. We'll call that AH. Since BC has length 25, solving for AH, we get 36 over 5. Let's call this point of intersection between our altitude and PQ. We'll call that point I. And we have triangle APQ is similar to triangle ABC. Comparing the altitudes, AI over AH is equal to PQ over BC. We can substitute and solve for AI. PQ is omega, BC is 25, and multiplying by AH, which is 36 over 5. The height of this triangle is 36 omega over 125. We have that PS is equal to our height AH, and we subtract AI and substitute. So now the area of our rectangle in terms of omega is PQ times PS. Now we'll distribute omega, and this is written in the format of the answer to the problem statement. The problem asks for beta, which is m over n, and we're asked to give m plus n, 36 plus 125, which is 161. One thing to notice about this starting inequality is that our upper bound is very small, considering that a and b are positive integers. Let's calculate some values of this fraction for various values of a and b. If we start with a and b are equal to 5, then our numerator is 26 and our denominator is 10. This is 2 3/5, which exceeds our upper bound. Let's try a and b equal to 4. Our numerator is 17 and our denominator is 8. And we get a value that is also greater than 2. Let's step down to a and b equal to 3. Our numerator is 10 and our denominator is 6. Now we're getting closer to our upper limit. So let's try a equals 3 and b equals 2. We'll remind ourselves meanwhile that our expression is symmetric in a and b. Here our numerator is 7 and our denominator is 5. And we get our first values of a and b that satisfy this inequality. Again, a and b have to be positive integers. So this only gives us a few values of a and b to try. Here's the expression we're trying to maximize. Let's try our highest values of a and b. Here our function is valued 6 1/5. Let's see what happens when a and b are smaller values. We see right away that our numerator declines a lot and our denominator only declines a little bit. This fraction is just a little bit above 4. And substituting smaller values of a and b is just going to make this value even less. So we have our maximum value. That's 31 over 5. And the problem asks for P plus Q. So our answer is 36. If you'd like me to solve any other AMC or AIME problems, please leave them in the comments.